Hello students, and welcome to the lesson and discussion on inequalities, exponents, and factors. Now before we get started, I just want to make one thing clear that this is really a review lesson, so I'm going to go through this fairly quickly. If you haven't seen this before, you should watch one of the other videos that will go into these topics in greater depth. So this is a review, so I'm not going to go too much into the proofs or the derivations of some of these laws. So let's get started with an inequality. And we all know that an inequality is an expression that represents that one thing is greater than something else or greater than or equal to. So let's just look at an example like this, like x is greater than, or I'm sorry, this x is less than 5. Okay, so that means x is all of the numbers less than 5. And we can write this in words. So x is less than 5, or we can also say, I'm going to put quotes around this. We say, all numbers less than 5. Okay. And we can also do this using mathematical symbols. We can also do this using by graphing. So we can write this using a graph, which is just a simple number line. And for my number lines, I like to put 0 on there. I like to put the numbers in question in there. And this is an open circle since it's less than, so it's not allowed to be equal to 5. And then it's going to point this way. Now, I know in some textbooks, this arrow here is right on the line. But when I'm doing things by hand, I like to just put the circle above it. And finally, we have a new way to represent this. This is called interval notation. And it expresses everything as an interval. So using this same example that we have here, x is less than 5, it would be all of the numbers in the interval between negative infinity, because x could be anything less than 5 all the way to negative infinity. And it can go all the way up to 5. Okay. Now it's important here that to point out two things. First is that the use of the parentheses. The parentheses represent exclusivity, meaning that it is not allowed to be equal to 5. That's when you use the parentheses. For example, let's look at a different scenario. Look at I'm going to call this one actually example 1. What if I had this expression as a graph? Okay, so if I had this expression as a graph, put 0 on here, put 7 on here, and then I'm going to fill in the circle and going it this way. What would this be in mathematical, as a mathematical symbol? Well, it's all things less than 7. The circle is filled in, so we know that this is x is less than or equal to 7. In interval notation, this would be everything between negative infinity and 7. But I'm going to use the square bracket here because it is inclusive. Okay, so I'm going to make a note here that parentheses mean exclusive, which means that it does not include this number. Brackets are inclusive, meaning that it does include this number. Okay, so that's really all there is to interval notation. It's just a different way of writing an inequality. So we have an expression like this where you have all numbers less than 5, or any number less than 5. We can write it using mathematical symbols. We can use it writing in words in a short English phrase or sentence. We can write it as a graph, and we can also write it using interval notation by giving it a lower bound. In this case, it has no lower bound, so we put a negative infinity, and an upper bound. Okay? And so this is going to be more useful later on in the year when we get to complicated topics, when we get into analyzing graphs and understanding their behavior. But these are all valid ways of expressing the same thing. Okay, so I'm going to put up a couple more examples. You should try to do this by yourself. and then hit the play button again to see if you got the right answer. Okay, so I have a few examples here, 2 examples, and the directions say write using words, symbols, graphs, and interval notation. So this is already written in words, so we don't have to write in words again. So we have to write this expression, any number not less than 2, using symbols, graphs, and interval notation. So again, if you should really hit the pause button, see if you can do this by yourself, and then hit play again. Okay? So here we go. Let's do this using symbols. So we're going to use x as our variable. So in this case, x not less than 2, which means that it could be 2 or it could be greater than 2, but it cannot be less than 2. So that means it's going to be greater than or equal to 2. Okay? Now in this case, I wrote the symbols first, but oftentimes it might be easier to draw this out as a graph. So we'll say 0 here, there's 2 here, so any number not less than 2. So anywhere to the left of this is not allowed. So starting at 2 is allowed, and anything greater than that is okay. So this represents anything not less than 2. Now, so this is using a mathematical expression with mathematical symbols. This is a graph. Okay, and let's look at what it looks like as an interval notation. Now, if you remember, we need a lower bound and an upper bound. So the lower bound in this case is 2, because it cannot be any lower than 2. And it is inclusive because it can be equal to 2. So we use the square brackets. Okay. The upper bound, well, it goes on forever. It could be anything. So we use positive infinity. And whenever you use infinity, we always put the parentheses in there because you can never really reach infinity. It's really an expression of saying that you're going to go on forever and ever. Okay, so that's a fairly straightforward example. Again, hit the pause button, see if you can do this next one. Any number less than 5 or greater than 8. So let's look at this. Okay. Any number less than 5. Okay. So that means x is less than 5 or x is greater than 8. Okay. And this is literally how we would write it using a mathematical expression or symbol, and we actually use the word or. As a graph, and I'll write graph on the side here. This would be, let's draw our line, put 0 on there, 5 on here, and 8 on there. It's not drawn perfectly to scale. So less than 5 means all the numbers starting at 5 and going to the left of it, so this could be less than that, or any number that's greater than 8. So now when we get into interval notation, this gets a little bit trickier. So let's just deal with this part. Anything less than 5. So it can start at negative infinity and go all the way up to 5. Let's deal with this part. It can start at 8 and go up to positive infinity. Okay. And the way we connect these two together is that we write a U in here, and U stands for union. So I'll make a note right here. This is union. And it is the interval notation way of writing this word or. Okay, so that's all that it really means. Okay, so just a couple of examples there of writing inequalities in different ways. And again, interval notation is what we're going to be using most in this class. The graph is really helpful to visualize these numbers and these inequalities, but we're going to use a lot of interval notation, especially as we get later on in the course, so we need to get familiar with it right now. So to continue our lesson here, our review lesson, we're going to switch topics just a little bit to laws of exponents. And again, I'm going to go through this fairly quickly. If you would like to see a derivation or some justification or proof of this, you should watch one of the other videos. This is a topic that's covered in Algebra 1 and Algebra 2, so we're going to review this fairly quickly here. So the first law that we have is x to the a times x to the b. So notice here, one thing is that this is the same base. Both of the bases are x. So when you have this scenario, it becomes x to the a plus b. That's one of the laws of exponents. Here's another one. If you have x to the a divided by x to the b, it becomes x to the a minus b. Next, we have, what if you have an exponent already, and the entire expression is raised to another exponent? So x to the a raised to x to the b, that's equal to x to the a times b. Okay. Next we have x to the 0 is always equal to 1 as long as x is not equal to 0. So any non-zero number raised to the 0th power is always equal to 1. And finally, this part here is a little bit tricky, but anything raised to the negative first power is really equal to its reciprocal. Okay, so x to the negative first power is really 1 over x. And two more of these to go. We have x to the, so if we have two bases, xy raised to the 8th power, then it's really the same thing as x to the a times y to the a. In other words, this exponent applies to both of the bases. And similar scenario when you have a quotient in here and you have an exponent, it becomes x to the a over y to the a. And so with these rules of exponents, and they're very important in pre-calculus, we're going to be using them a lot. We can do a lot of examples, and we can do a lot of simplification that will make things better for us when we try to solve these problems. So I'm going to put up a few more examples. And again, for all these examples, you should try them, hit pause, try a few others, and then see if you can compare your answers to my answer. All right, so I've got 4 examples here that we are going to do. And again, I'll suggest that you hit pause, complete them on your own, and then compare them to my notes and make any corrections that you need. So this we have 3 to the 2nd power raised to the 5th power, and I'm just going to write the law of exponent on the side here. This is applying the law x to the a raised to the bth power. Okay? And if you remember, this is x to the a times b. So in other words, we are going to multiply these two exponents. Okay, so 2 is like a in this case, and 5 is like b in this case. So this becomes 3 to the 10th power. And usually this is sufficient. You can certainly plug this into your calculator and get a huge number, but it's cleaner and more helpful to us many times to view it as this way, seeing a prime number as the base and then some sort of exponent. Okay. Next, for part B, we have 3 to the 2nd times 3 to the 5th. So this is really applying the rule x to the a times x to the b. And if you recall from the last set of notes, this is x to the a plus b. So we add these two together, and you have add these two together, and you have 3 to the 2nd plus 5, which is 3 to the 7th. Okay. Now here we have an example that's combining several things. We have an exponent raised to another exponent, but not only that, it's a negative exponent. So first thing I'm going to do is apply this rule right here, and this is going to be up here, this first rule that we just used for part A, and this is going to become 3 to the negative 6th. Okay. Now we can leave this like this, but this is not really standard form. When you write exponents, everything really needs to have a positive exponent. Okay, so just remember that. Every final answer must have a positive exponent. There should not be any negative exponents in your final answer. So we have to find some way to convert this into a positive exponent. And so what I'm going to do is use this rule here, but do it backwards. So I'm going to say that this is really 3 to the 6th to the negative first power. And the reason that that I do this is that I can separate the 6 from the negative 1, because we have a nice rule that applies to negative 1. So if you remember, any number to the negative first power is really the reciprocal of that number. So here, 3 to the 6 to the negative 1 is really 1 over 3 to the 6. And so that turns out to be our final answer. So let's try this one here. We have a quotient and then an exponent. So I can apply this rule here where you have, it's called x over y to some power is really x to that power over y to that power. Okay, so this is what we talked about before. So I'm going to do this here. This is going to be 2 to the third over xy to the third. So applying this power to the top and the bottom. But you have to be careful that when you apply it to the denominator, because you have a product here, put parentheses around it. Okay, otherwise, you're going to get into some errors. So the top here is pretty much done, as simplified as it possibly can be. The bottom, though, we can take it a few steps further. And if you remember this rule, that anything to a power, any product to a power, is really each one of those bases to the power. So x, y, quantity to the 8th power is really x to the a times y to the a. So we can take this a step further. The top is still 2 to the thirds, and the bottom is x to the third, y to the third. And so when you work through these problems, it's really, sometimes it's tough to tell when you're done or when it's simplified as much as possible. The way to tell it is, again, there should be no negative exponents, okay? And any bases that you can combine, you combine them together. So you have two bases like this. You have a 3 to the second, 3 to the fifth. They should be combined into one single base, just 3, and then the exponent. So I'm going to put up a couple more examples here of this, just so we get the hang of it, because this can be tricky. Okay, so here you have another example of simplifying exponential expressions, and we got a lot of things going on here. We got multiple variables, we have a quotient here, and then we have the whole thing raised to a power, and not only that, a negative power. And so there's many ways that you can do this problem. I am going to do this by simplifying what's inside here first. So some people like to take this -2 and just multiply it out to all of these exponents, and that's perfectly fine to do. I like to see if I can simplify what's inside the parentheses first. Okay, but again, if you do this a different way, as long as you follow all the laws of exponents, we should both arrive at the same correct answer. So the first thing that I'm going to do here is just look at the inside of the parentheses and just separate it into two different parts, okay? Because I have x's here, that's one base, and I have another base, which is y. So I try not to mix those two together. So this is really equal to parentheses x to the 4th over x to the 9th times y to the 9th over y to the 3rd, and the whole thing raised to the -2nd power. Okay, so again, this is just a matter of separating this into two fractions. So if you multiply these two fractions, you get this answer up here. Okay. And then we can simplify each one of these separately. So if you remember this rule, x to the a over x to the b is equal to x to the a minus b. So in this case, you're going to have x to the 4 minus 9, which is -5, times y to the 9th minus 3, which is y to the 6th, and the whole thing raised to the -2nd power. Okay. So taking this a step further, where we apply this exponent to both of these, so I'll remind you here with this rule, x to the a times y to the a, and the whole thing raised to another power. Well, we just multiply this by each of these. Okay. So this is going to be x to -5 times -2 is +10, +6 times -2 is -12. Okay. And again, just be careful. I'm going to make a note here that all exponents should be positive. Okay. So the x to the 10th is perfectly fine, but the y to the -12th is problematic. But if you remember, we have a rule for doing that, and it's really just the reciprocal of y to the positive 12. And then once I'm all done with everything, I like to put it all together into one fraction. So it's going to be x to the 10th divided by y to the 12th. And there you have it. That is our final answer. Okay, so we have one more topic here in our review session, and that is expanded form versus factored form. And really, this is just a matter of notation and vocabulary, just a matter of how we write the expression, but the expression means basically means the same thing. So, for example, expanded form would be like this when you have multiplied everything out. Okay, so x to the a x times a plus x times b. That's expanded form, where you have a product plus another product. But we know from prior algebra classes that this expression can be factored because it has a common factor, which is x. So we can factor that out. We get x times quantity a plus b. Okay? And so that's mostly all there is to this topic. So let's just look at a quick example here. We'll call this example 5. And we're saying write in factored form. And I'll give this example as 7y plus 14y to the third. So we can identify the common factors, which is 7. 7 goes into both 7 and 14. So we can pull out a 7, and that leaves us with 1 and plus 2. And then we also see that there's y here is also a common factor. It goes into both y and it goes into y to the third. So this gives you 1. We'll pull the y out there. Okay, so this is the common factor goes outside of the parentheses, and whatever is left after you divided it out, and you pulled out a y here, so you're going to end up with y to the second power. So there you go. You have an example. This is factored form. This is expanded form. Let's take a look at one last example. Let's say now we have write in. I'm going to write this on the margin here so we get more space to work with. This is going from factored to expanded. So x plus 5 times x minus 3. Okay? So this is factored form. These are two factors. Okay, this is x plus 5 is one factor, x minus 3 is another factor, and we want to expand them. So if we want to do that, well, let's just multiply and distribute everything out. You're probably familiar with this as FOIL, but this is more general concept. FOIL definitely works for this example, but this is just the distributive property. So multiply x times x, you get x squared, x times negative 3, negative 3x, 5 times x, positive 5x, and then 5 times negative 3, negative 15. We simplify it, and you get x squared plus 2x, because these two terms are like terms, minus 15. So here you have it. Factored form, expanded form. Expanded form, factored form. Okay? And so we'll be using these words and this vocabulary a lot, factored or expanded, and this is basically what it means.